Hi, I'm Jose Abel, civil engineer. So one of the things that's important for civil engineers who are constantly using computers is to know what to expect out of their hardware, out of their computers. I teach a course here in Chile at Universidad Los Andes on computational methods for civil engineers. And one of the things I teach them is to do benchmarking of their systems so they know what to expect from their systems. Today I'm going to be talking about input-output of scientific data. Scientific data is matrices, arrays, those kinds of things. So we're going to be doing a little scripting, and I'm going to be talking about storing and the benefits and trade-offs between three different file formats. The first one is going to be a text-based format. A second is going to be NumPy's NPC data format and direct binary. Okay, so here I have a little Python script, and you can see I'm importing NumPy as NP. I'm going to be writing random matrices, so I import the random function, and we're going to be doing some timing. So I'm going to be importing the performance counter from the time module in Python, and OS is going to be allowing us to essentially take a look at the file sizes in disk without looking at the folder. So okay. So let's start by creating a random matrix, n by n matrix of size 1000 by 1000 using the data type double. Okay, a double, just so you know, is 8 bytes per number. Okay, so that'll be 64 bits per number. Okay, so the first thing, I create this matrix, and then let's figure out the memory use of this matrix. It will be the 8 bytes times the size of the matrix, which is n by n. The way to do this in Python would be to say the d type is the data type of the matrix A, and the item size field is going to give me the size in bytes of one element. And if I multiply that by the size of the matrix, which is n by n in this case, I get the total amount of memory use in bytes, and I divide that by 10 to the 6 to get a number in megabytes. So, and then I print out the memory use in megabytes. Let's put a little exit here and execute this code. So memory use for an 1000 by 1000 matrix is 8 megabytes. So now I'm going to be writing this matrix into text first. So let's unroll that bit of code, and I'm going to be writing this into a text file using this a.txt or the save text function from NumPy. So this text file, you can see, is 19 megabytes. That's what the OS is reporting here, 19 megabytes in size. And I can open this file in Sublime Text right here, and you can take a look at the numbers in here. So that's fine. I'm storing 17 decimal places, and that's what this format specifier here is doing. It's telling the save text function to store 16 decimal places. Okay, what's weird is that the memory, in memory, it's 8 megabytes. That's what my RAM is doing, but the file size is 19 megabytes. And the reason for that is that each of these characters in this file is about 2 bytes in size. So you can see if this number, storing this number, is 18 characters, and each of those 18 characters is 2 bytes, I'm going to be using 36 bytes to store this number. But this number is a double, so in memory it's only 8 bytes. So this text file format is not very efficient, and it's also not precise because I am truncating the decimal places here. So when I load back the matrix, I actually lose some information by storing into a text file. So let's move on. Next up, I'm going to be loading that matrix. So in this part, I am reading the matrix. You can see you use save txt to store the data, and then you use load txt to load the data. Now you can also see that I'm using perf counter to measure timings. So how much time it takes to store the matrix and how much time it takes to read it. It comes from the difference between these timings over here. So the next part of my code actually uses that information to get a sense of the performance. So the rate of writing is going to be the memory used, so the 8 megabytes divided by the interval in time. That's going to give me a rate in megabytes per second. And the read is going to be the memory use of the matrix I'm reading over the time lapse between these 2 points. Okay. Additionally, you can see the disk use in disk. I am getting it from using os.path.getSize, and I'm giving it that file and dividing by 10 to the 6 to get a number in megabytes. Okay. So with all of that, I can report nice and easily the rate and the disk use and everything. So you can see we're writing at 14 megabytes per second and reading at 15 megabytes per second, and we're storing 19 megabytes where our actual information is 8 megabytes. So the information you want is 8 megabytes, but you're writing 19. So this makes text files very bad file format for large data sets. It's not only slow, but it's also large. It's inefficient. So let's move on to our next file format. The next file format is NPC. This is NumPy's basic way of reading and writing datasets. It's very versatile. You can store many arrays in one single file, and it stores the data in binary, in a binary representation. It also stores some metadata. I'll talk to you about that a little bit later. And it also compresses the data set. So it takes the binary representation of the file, ones and zeros, and stores it in a zip file, essentially. So when I run this, you can see now the a.npz file. Let's ignore this. It's complaining about this file that has changed. The npz file is actually reported as a zip file. From my OS reports it as a zip file. If I can open it with the Archive Manager and see that there's a .npy file in there, which is a binary representation of the file, plus metadata. So it knows about the size of the matrix and the data type. It also stores that information. So you can see if I now ask for the disk use for this file, let's bring it down. So now I'm using getSize to get the size of this npz file and also recording the rates. Let's take a look at what happens now. So I get much faster, much higher rates. So 364 megabytes per second and 500 megabytes per second for read. And I get a file size in disk, which is a bit higher than the 8 megabytes stored in memory. And the reason for that is because what I told you, NPC data format actually stores metadata. So the size of the matrix and the data type, among other things. I don't know what else, but it might be a few other things in there. Okay, so this NPC data format is actually more efficient than text, and in speed, and it also uses up less disk space. So it's a win-win. What you do lose is the capability of looking at the data set by yourself in a text file. So if you open it up in Sublime Text, it's going to say binary down here. And okay, that's a small loss. But when you're reading and writing large data sets, it's actually very convenient to use NPC. What's next? Next is binary. So binary is just taking the ones and zeros representation of the data set in your memory and storing it directly into disk and then reading that back up. So it's a bit more involved. This is how you write a binary file. It's actually very simple. A to file a.bin, and that's it. And then next, to read it, though, because the binary data format does not store the data type and the shape of the matrix, you actually need to incorporate that information. You need to know it up front. So a.bin is going to be from file a.bin, and then you need to give it the data type that you're reading, and then you need to get this array, which is going to be a 1D array, and you reshape it into the size that you want. So you need to know a priori the data type and the size of the matrix you're reading. After that, we can get rid of the exit and do the same computations, get the disk use and the rates and report the whole thing. So you can see now for the binary, I get exactly 8 megabytes of data. That's all I'm storing, the exact representation in memory, but a huge performance boost in reading and writing this data format. So this is quite amazing. I go from writing the same data set at 13 megabytes per second, if I'm doing that in text, to something like, this is 1 gigabyte, 1.4 gigabytes per second if I'm using binary. I can run this and I can see if I get performance boosts. You can see my reading rate is actually impressive, is 2.8 gigabytes per second for the reading. This is very hardware dependent. Right now I'm in my laptop that has a nice M.2 disk that I can write solid state disk directly into the PCI Express lanes. So that means I can read and write that data format directly. If the matrix that I'm writing has a different structure that performs a bit better. So let's say instead of this matrix, I'm going to use an identity matrix. Let's data type. Let's say np.I. This is just ones along the diagonal and a whole bunch of zeros. So it's a very small information matrix. Let's do it like this. So what are the results now? Let's see. So in this case, let's take a look. It's pretty much the same. I was expecting it to be better due to the compression algorithm, but actually the compression is not doing much for this data set. In this case, I was expecting, because it's an identity matrix, the low information, the compression algorithm was going to perform better, but actually it doesn't, and I'm a bit surprised at this. I guess it's going to depend on the system. Now, what happens if, like, the a.txt is just a whole bunch of zeros? So I can grab this a.txt, let's compress it directly with a zip file. And if I do that, it goes from 19 megabytes to 51.7K. So this is interesting. So in this case, it might actually be better to write as text. If you want to store this matrix or this type of matrix, for some reason you want to store an identity matrix, not very good, but you just write it as a text file and then you zip it, and then you get an incredible performance gain in as far as this is concerned, in disk use, right? If you could do this in one go in memory, you might see some performance gains. But for now, this is all I want to talk to you guys about. If you like this video, please give it a like, subscribe, leave me your comments below, because if you like these types of videos, there's more ideas I can share with you. Until next time.